Hello. So in today's video, what we'll discuss is that what is the mass of an electron when it moves under the impression of an external electric field inside a periodic lattice. So that mass is usually different from the rest mass of the electron, of a free electron, which is 9.1 into 10 to the power minus 31 kg. So in this video, we will see how we define effective mass, what is the formula for effective mass, how does it vary with the E and K relation, and what is the physical significance of negative effective mass and other things. So here I have drawn the very simple model of one-dimensional periodic lattice. So this is the arrangement of let's say ions at these sites in a periodic one-dimensional lattice. Now we know that the energy, potential energy is for, suppose there is a 1 unit charge here and the electron is moving in this direction under the impression of the electric field E in this direction. So because electron is a negatively charged particle, so if the applied field is in this direction, electron will move in this direction. So under such circumstances, the electron has to actually face these potential barriers. This is the chronic bending model for the same one-dimensional periodic lattice, because if we observe that this potential energy, this is the graph of the potential energy, if this R, if we go from this away from this point, from the location of this ions away, so this varies as 1 over R, it drops down as 1 over R. Similarly, this is true for this side. So we get this kind of actual potential in the one-dimensional lattice, which was modeled by Kronig-Penney to solve this kind of potential, the Schrodinger equation with this such kind of potential, and they gave a Kronig-Penney model that this actual potential actually can be replaced by, can be approximated by with this kind of rectangular potential barrier, and retaining the periodicity of the lattice. And so what will happen when electron moves under the impression of electric field applied in this direction, electron will move, get accelerated in this direction. So what will happen? We know that the de-Broglie told us that whenever a moving particle is there, it has a wave associated with it. Rather, a wave packet is associated with the motion of an electron or any microscopic subatomic particles, for example. So if the electron is moving this side, this wave packet, associated wave packet, is also moving this side, which has a velocity which is known as a group velocity Vg is equal to d omega by dk, where omega is the angular frequency. And we know what is the energy of a free electron. Energy of a free electron is h cross k square by 2m, where m is the usual mass of the electron. P equal to h cross k is the momentum, and E equal to, energy, epsilon is equal to h cross k square by 2m, p square by 2m essentially. And we also know that there is another formula given by the de-Broglie for the energy of a free particle. This is free electron equal to h cross omega. So if I calculate from this relation that d omega by dk is actually equal to h cross k by m. The h cross is the momentum of the particle, and this is the mass of the electron. The particle is electron in our case. So P, this is essentially the velocity v of the electron itself. So Vg is equal to V. It means the wave packet moves with the same velocity as that of an electron, which is sensible. If it is not the case, the wave packet will go ahead, or it will left behind from the particle if it is not equal to the velocity, if its velocity is not equal to the velocity of the electron itself. Okay, so this is the first conclusion that we draw. The second case is, now since we have applied the external electric field in this direction, so it will try to accelerate the electron in the in this direction. So it will change its kinetic energy. The electron will gain the kinetic energy due to the applied electric field. What is the change in the energy of the electron due to this applied electric field E? This is the work done by the field on the electron. What is the work done? Work done is force into displacement. Force is E into E, and displacement is, let's say, in dt time, the displacement of the electron in this direction is dx, which is from left to right, from my left to right, this direction, dx. So if I multiply it by dt and divide by dt, so I can actually write down EE dx by dt into dt. Now dx by dt is the velocity of the electron, which is v into dt. Now since v is equal to vg, I can actually write this as vg. So let me write down this equation as 1. Now there is another way of calculating this change in kinetic energy of the electron, change in total mechanical energy of the electron. What is that? The change in kinetic energy of the electron can also be calculated as d omega equal to h cross epsilon is equal to h cross d omega, because epsilon is equal to h cross omega. We have just used that, and if I differentiate it, d epsilon is equal to h cross d omega, change in the energy will be given by this relation also. If I further multiply and divide by dk, so this will becomes h cross vg into dk. If I compare 1 and 2, I get the following result: E upon h cross is equal to dk upon dt. So that's what we get. Now there is another way of writing down group velocity Vg. We have just seen that Vg is actually equal to d omega by dk. So if we write down, so if I rewrite my Vg in the term, in the form of d epsilon by dk, because if I multiply and divide by h cross omega will become d epsilon and d epsilon by dk. If I take the time derivative of this relation here, dvg by dt, which is eventually equal to dv by dt, because vg is equal to v, is equal to 1 over h cross d over dt times d epsilon over dk, which can be further written as 1 over h cross dk by dt into d2 epsilon by dk2. This is equal to this if I multiply it and divide by dk. For example, this becomes dk by dt and this becomes d over dk2. Now dk over dt we have just calculated as E by h cross. If I replace here, so this becomes 1 over h cross E by h cross, which has become h cross square. I have replaced dk by dt, E by h cross, so E by h cross square into d2 by d2 epsilon dk2. So if I see, this is acceleration of the electron. V is nothing but the velocity of the electron. So dv by dt is nothing but the acceleration of the electron. This is the acceleration of the electron. Let me write down AE. And this is force here, because this is the force due to the external electric field E. So force upon something is equal to acceleration. That something has to be mass. So let me write down this as m star. So if I read this relation as this, so this simply gives me that m star, if I compare, for example, let me put as 5. So if I compare 5 with this standard Newtonian equation, this m is equal to h cross square divided by d2 epsilon by dk2 as x. So this is what we get as a formula for effective mass. Now from this formula would we observe that the effective mass depends on this d2 epsilon by dk2, because h cross is a constant. Now when we solve Schrodinger equation for such kind of a model of one-dimensional periodic lattice, we get a relation between E and K, which we can plot, and after plotting we get this kind of graph. So what we see from this graph, that this region here, minus pi by a to pi by a, which is known as first Brillouin. This is known as first Brillouin. This region here, and this region from this here to from pi by a to 2 pi by a, and from minus pi by to minus 2 pi by is known as second Brillouin, for which the graph is as this. So if we concentrate here, for example, near this region of this graph or the center of the first Brillouin-John, which is nothing but the origin of this graph, we concentrate near to this. This behavior is a parabolic type. Now we already know that the energy of a free electron is epsilon equal to h cross square k square by 2m, which is nothing but the parabolic behavior if we plot T and K. Means near the vicinity of the origin or near the center of the first Brillouin-John, this electron behaves like a nearly free electron because its energy is approximately equal to h cross square k square by 2m. So if we calculate from this relation d2e by dk2, we will approximately h cross square by m. So if we differentiate it twice with respect to k, we get h cross square by m, because in the first differentiation we get 2k, 2 cancel out, the second differentiation k will become 1. So this will become h cross square by m. So if we compare, if we put this value, for example d2 epsilon by dk2 here in this expression, we get m approximately equal to m star. So it means what? When electron is near the center of the first Brillouin-John, it behaves like almost like a free electron. So that its mass is almost equal to the mass of the free electron. However, if we come to this point where this curve actually changing its nature from let's say convex to concave, it is changing its nature. So what we observe at this point of inflection, we know that the d2 epsilon by dk2 will be 0. It means the effective mass will be infinite. The meaning of this infinite effective mass is that electron is has become an object as if it has an infinite mass, that it is not being able to move at all because of this electric field that we have applied and the forces that the field that is filled inside the lattice when it moves from, let's say, from this direction to this direction. How does it happen? What happens actually physically, it can be thought of as this: when electron is moving from this direction to this direction, its de-broglie wave is also moving this direction. So when electron is around this point, so this, what happens that the reflected wave from these barriers, the reflection of the de-broglie wave from this barrier will become more significant. When electron is at the center of the first Brillouin-John, this reflection is not a very significant one. But when, as you approach to this boundaries of the first Brillouin-John, this reflection becomes more and more significant. So the effect of this reflection is when de-broglie wave is moving this direction, it gets reflected back in this direction. So it gives a momentum in the reverse direction. So when this moment in the reverse direction becomes almost equal to the momentum in the forward direction that was given by the external electric field, so the electron doesn't move at all. So it behaves like as if it has an infinite mass. So that is the interpretation of the infinite effective mass. Now if we go on further, so here I have just concluded that m star is almost equal to m. Here m star is infinitely, it is infinite, and if we go very close to this k equal to pi by a, then what happens that this becomes d2 epsilon by dk2 from graph, it becomes negative because it's a maxima here of the graph, and for maxima we know that d2 epsilon by dk2 has to be negative. So this will become negative, the effective mass becomes negative here. So here it becomes negative, m star is negative. But how can we understand that physically? Mathematically it is clear because this is negative, so m star is negative. But how can we understand it physically? The same way, when we reach to this edge of the first Brillouin-John, what happens? The reflection becomes so significant that the linear momentum obtained in the reverse direction dominates on the linear momentum in the forward direction. So electron is moving in the reverse direction now, which external electric field would have forced to move in the other direction. So electron behaves as if it has a negative mass. That is the interpretation of negative effective mass and zero effective mass, and the usual effective mass being equal to the mass of the free electron.